this video, I would like to talk about the steady-state response and steady-state performance in a closed control system. Okay, so in order to understand or compute or measure steady-state response of a control system, the fundamental knowledge that you need to know or remember is final value theorem. Okay, if you remember from your differential equations or signals and system courses, you should know that limit when t goes to infinity, okay, x of t is equal to limit when s goes to 0, s times x of s. Of course, we know that this equality isn't always equal to each other. Under some specific conditions, they are equal. What are the conditions? If you remember, if you look at x of s and if we write its pole zero plot, okay, first of all, there shouldn't be any poles in the open right half plane. So it's very simple, because if we have a pole in the open right half plane, okay, we will have an exponential which has in the form of e to the power alpha t. If alpha is positive, it will blow, and the final technically the actual limit will be infinity. But if we compute this, we will have some number which is not equal to infinity. Okay, so there shouldn't be any unstable pole in the x of s. Okay, it's one requirement. The other requirement is there shouldn't be any pole, okay, on the imaginary axis except the origin. The origin is fine. This final value term is still available if we have a pole at the origin. Okay, a single pole actually. There should be only a single pole. But if you have a pole on the imaginary axis, the final value term will still give you a wrong result to you. Okay, so technically, what we want from a system is, okay, so because we are trying to find steady-state error or steady-state performance in a control system, we want the system to be stable first, because it's our main requirement. Then we can start talking about the stability, not stability, steady-state error or steady-state performance. Okay, so keep in mind that final value theorem is the fundamental knowledge or technique that you need to know to understand this lecture. Okay, so now let's talk about a closed loop control system. Okay, in a typical feedback loop, we have a structure like this. We have a reference signal R of t, output signal Y of s. Okay, so we have G of s, which is technically in the upper part of the feedback diagram, and in the feedback loop, we have H of s. Okay, that's it. So what is error? Okay, in a feedback loop, we can assume that error is error between y and r, which is slightly correct. But the better way is looking at the error is looking at this difference, because what is error? Error is the difference of two operations, two technical signals, right? And this is where we technically compute error in real time. Okay, that's it. This is the error. So this is our error signal. Okay, and in general, H of S is called the transducer or sensor dynamics. And this operation that we do in a control loop is technically the where we look at error between the reference and our measurement. And this is the signal that we try to minimize or technically equate it to zero as fast and as best as possible. So in the steady-state performance, tracking performance part, we will concentrate on this signal. Okay, so we have error steady state in time domain which look like this. Okay, E of t. Okay, under the condition that the closed loop system is stable, we can technically use this final value theorem. Okay, S times E of S. Okay, so what is E of S? Okay, let's try to write E of S in terms of the input signal and the transfer functions. First of all, we know that E of S is equal to R of S minus this signal. So what's this signal? E of S, G and H. E of S times G of S times H of S. Okay, so in that respect, we know that E of S is equal to 1 over 1 plus G of S, H of S times R of S. That's great. Okay, so this transfer function, okay, is the transfer function from the input to the error signal. And we want this transfer function to be small in general for a good closed performance. And we will try the technical concentrate on the transfer function to compute the steady-state error and characterize steady-state performance. Okay, so we call this transfer function as the open loop transfer function of the system. So what is open loop transfer function? Open loop transfer function is transfer function from error signal to the entrance of the feedback signal or a feedback operation. So if we call it f of s, okay, transfer g s times h of s is equal to transfer function from error to f of s. So what is this? E of s is equal to 1 over 1 plus GOLS. We call it the feed forward or open transfer function of the system. That's great. R of S. Now, using this, let's try to compute steady state error, right? We can do that. Okay. So steady state error states that under stability assumption, of course, is equal to limit ns goes to 0. Okay. S times, right? 1 over 1 plus GOLS times R of S. Of course, it depends on input, right? Because input, it changes the output behavior, and we need to take into account the input. So what is the most important input? Of course, it's the unit step input. In general, in control systems, step inputs are super important because reference signals, in most of the time, not always, are in the form of some sort of constant, right? We want to go to a specified speed. We want to go to a specified position. Okay, so it's step input. Okay, unit step input is just a test signal that we try to characterize. Okay, so if we compute the unit step steady state error, we know that R of S is equal to 1 over S. In that respect, it will be simply equal to limit when S goes to 0, 1 over 1 plus GOL S. That's great. Okay, so before going into like deeper analysis, let's analyze this quick a little bit. Okay, so GLFS is technically a rational function, right, in S domain. So a polynomial in S and the polynomial in S. So we just plug it at S to obtain a number. Okay, so let's assume that this is constant, okay, such that GOL 0 is equal to KDC, right? In that respect, we know that steady state is error equal to 1 over 1 plus KDC. So KDC is the DC gain of the system, if you know it from your circuit classes or signal system classes. This is my steady state error. That's great. Okay, so now I have a relation between steady state error and a system property KDC. So if I have a control on KDC, what I can do that error, I can drop steady state error, okay, by increasing the DC gain of the system. That's great. I think it's really, really great because it means that I have a control on steady state error. If I want steady state error to be perfectly 0, what I need to do is KDC should be equal to infinity, and then error steady state will be equal to 0. Of course, this is true for the unit step input. Actually, this really summarizes everything about steady state performance. Okay, any other thing will be just kind of extension or technically a discussion of this simple analysis. Okay, you don't need to memorize anything. You only need to remember final theorem and the simple steps that I performed in this example. Okay, now let's try to technically analyze this steady state error in a more deeper fashion. So what we do is we write GOLS in a more standard form, in a different form, such that we can easily characterize steady state error, such that we have a constant K, okay, under some assumptions, or like case this can be the DC gain of the system, okay, S to the power n, so this is critical, okay, so some S, we have an integrator to the power n. So what I do is I isolate the integrators from the other part of the system, and let's call it n star of S, the star of S. Of course, what is star? And I know that n star of S divided by the star of S when S is equal to 0 is just equal to 1. Okay, so this part, of course, it is composed of bunch of zeros and poles, but we know that when I plug S equal to 0, this is just 1. So in that respect, okay, GOLS is characterized by a constant, okay, a constant, a free integrator, okay, bunch of integrators, okay, of order n, and a transfer function form, or like rational function, where we plug S equal to 0, it will be equal to 1. Okay, so this part is super useful to characterize steady state performance. And what we do is n, we call n as the type of the system. Okay, system type. Now we will talk about a type or characterized system based on the order of n. So if it is 1, we say type 1 system. It is 0, type 0 system. Okay, if it's 2, type 2 system. That's great. Now what we will do is we will try to technically characterize the steady state error based on the type of the system. Okay, so let's go back to the previous case. We previously derived that under unit step input, error steady state is equal to limit when s goes to 0, okay, 1 over 1 plus GOLS, right? Okay, so let's have a look at this. Okay, when s goes to 0, this is equal to 1, so I technically rewrite this like this, so it will be the same thing. Okay, now I really have a much easier path. Okay, now let's analyze this under different types. Okay, that's great. So if n is equal to 0, okay, type 0, n equal to 0, if let's change the color, error steady state is equal to 1 over 1 plus k. Okay, that's great. Okay, so for a type 0 system, I call k as kp, which is also called static gain constant of the system. Okay, so this means that if I have a system of a type 0 system, if my input unit step, I have a constant steady state error, okay, and it's equal to 1 over 1 plus kp. And what should I do in order to improve the steady state performance? I need to increase kp. If kp increases, error steady state decreases. And if I want to make error steady state 0 under this assumption, I need to have an infinite gain, which is practically not possible for a type 0 system. Okay, that's great. So, okay, that's nice. So what we need to do is, okay, so let's assume that I have type n system, okay, where n is greater than 0. It can be 1, 2, or 3. Okay, in this case, error steady state is equal to limit, okay, 1 over 1 plus, okay, when n is equal to 1 or 2, this will go to infinity, and error steady state will go to 0. That's super great. Now I have a 0 steady state error. Okay, so if we summarize for unit step input, I have two cases. Type 0 system and type n system where n is greater than 0. I have a constant steady state error, which is equal to 1 over 1 plus kp, where kp is simply equal to k, and we call it static error constant or positional error constant. It depends on different textbooks. And for type n system, where n is equal to 1, 2, 3, or whatever, is equal to 0. That's great. Okay. So if you want a perfect steady state error, okay, under unit step input, it says that you should change the type of the system, which you can do by changing your controller type. If you're okay with constant state error, but if you try to minimize it, what you can do is you can change the static error constant of your system. Okay, that's great. So what is the next important input, okay, that you can use to characterize the state error or state performance of the system? Of course, it is unit ramp input. Okay, such that r of t is equal to t times h of the unit step input, or let's say t is greater than equal to 0, and it's equal to 0, and t is less than 0. And we know that the Laplace transform is equal to 1 over s squared. Okay, that's great. So if I compute error steady state, it is equal to limit s goes to 0, okay, s times r of s, and of course the technically the open transfer function of the system. I can write g all of s, but let's rewrite in the simple form. Okay, so we already tried the form, the standard form. Okay, k divided by s to the power n, and I know that I have other parts. Okay, this, but if I just plug s, equal to 0, it will be equal to 1, so I really don't need to write that. Okay, that's great. So error steady state for unit ramp limit s goes to 0. Okay, so this is technically like this, s like this. Okay, 1 over s plus k to power s to power n minus 1. Okay, that's great. I think that's fine. So when s is going to 0, this is going to 0, so it is equal to 1 over, okay, limit s goes to 0, k divided by s to power n minus 1. Okay, that's great. So now let's analyze this a little bit. So if this part is constant, okay, I have constant state error. But before that, let's analyze based on type of the system. So what is the simplest type? N is equal to 0, type 0 system. So what's happened if n is equal to 0? Okay, so let's analyze this. S to power minus 1, so it is s. So this part is going to 0. Okay, it's interesting. Error steady state is going to infinity. Okay, so that goes to infinity. Okay, so what happens when n is equal to 1? When n is equal to 1, this is to the power 0. Error steady state is equal to 1 over k. So under this case, we rename k as kv, or which is velocity error constant. As you can see, we have constant steady state error. When n is equal to 2, let's say, or larger, if we compute steady state error, so it will be s to the power 1, 2, or something like this. Okay, so in that respect, this will go to infinity. 1 over infinity is equal to 0. Okay, so when we have a unit rep input for a type 0 system, we have infinite steady state error, which means that it is bad, right? It is simply bad. But when n is equal to 1, we have a type 1 system. I have a constant steady state error, okay? And steady state error is equal to 1 over kv, which is the velocity error constant of the system. And if I have a type 2 or higher order system, higher type system, my steady state error is perfect, which means that it is equal to 0. Okay, the simple extension of this unit ramp, which is not used much, is unit acceleration input or unit quadratic. Okay, unit quadratic or unit acceleration input, where r of t is simply equal to 1 over 2 t squared. Of course, t is greater than equal to 0. It's equal to 0 when t is less than 0, which has Laplace transform of 1 over s cubed. Okay, so if I follow everything, if I compute steady state error, which is equal to limit when s goes to 0, okay, so s, r of s, 1 over s cubed, okay, and if I write it in the standard form, this is equal to s to the power n. Okay, that's it. I have other things, but they are not important, because when I plug s equal to 0, other parts will be equal to 1. So if I compute error steady state, it is simply equal to, okay, 1 over, okay, limit s goes to 0, k divided by s to power n minus 2. That's great. Okay, this is steady state error. So let's analyze it. Okay, so if n is 0 or n is equal to 1, okay, in both cases, it will be s to the power minus 2 or s to the power minus 1. If I plug s equal to 0, this part will go to 0. Okay, so 1 over 0 is infinity. So error steady state is equal to infinity. So it means that, so let's clean that. If type of the system n is less than or equal to 1, okay, I have a terrible steady state error. It is infinity. Okay, so you should keep in mind that this doesn't mean the system is stable, because I have an input that is unbounded. It's also possible to obtain unbounded output or unbounded error signal. Okay, it means that the error between the reference signal, or difference between the reference signal and the technique, the measurement, goes to infinity. It is not convergent, it's divergent. Okay, so if I plug n is equal to 2, which means that I have type 2 system, okay, this will go to 1, so it will be equal to 1 over k, and we call it ka, right? If I remember, ka, which we call it static acceleration constant, which means that I have a constant state error. Okay, if n greater than 2, which have type 3 or 4 system, error steady state is equal to 0. Okay, so that's it. That you need to really know about the steady state error performance, tracking performance in a closed loop control system. Okay, the only thing that we did, only magical thing that we did is the final value theorem. So what we did is, using final value theorem, we characterized our transfer function in a specific form, which is given here. Okay, we generated a definition which is called the type of the system, and we computed the steady state error by looking at the type of the system. So if you don't remember any of these things, what you can do is you can simply go to the basics, apply final value theorem, and you can always compute the steady state error and talk about the performance. Okay, that's great. So let's solve an example to better understand the steady state error performance and characteristics. Okay, that's nice. So let's look at, remember our previous feedback diagram in the previous lecture. Okay, that's great. So I have KP. That's good. Okay, minus. So this is 1 over S. Okay. So I have KD here. Sorry for that. Okay. This is 1 over S. This is my output, of course. And again, so since I have two loops, okay, inner loop and outer loop, when we talk about steady state error, I always talk about the outer loop because this is my reference signal. I don't technically I care this also, but the main error signal is this, okay, not this. Okay, so it's important. Sometimes you can just mix this. Okay, that's great. So what is the question? First of all, the question asks the type of the system. Okay, just define the type of the system. So what we need to do is, in order to compute the type of the system, we need to find the transfer function from this point to this point. It's very easy. So we first need to technically simplify the inner loop, and we will find the outer loop. So what is the inner loop? And we already defined it in the previous lecture. It is equal to, okay, so 1 over S plus KD. Okay, that's great. So GOLS is equal to KP divided by S plus KD. So what is the type of the system? Type of the system is determined by the free integrators, okay, or number of poles at the origin. This is a type 1 system. Okay, that's great. And then the question asks that compute the steady state error to unit step, unit ramp, and unit quadratic inputs. Okay, that's great. So it's a type 1 system. Okay, so let's start with unit step. Okay, so if you remember the derivations for a type 1 system, is steady state error to unit step input is equal to 0. That's easy. Okay, so for unit ramp, okay, steady state error is equal to 1 over kV. What is kV? kV is technically what we do is we isolate integrator, okay, and we compute the limit, or we replace S with 0 for the limiting part. So kV is equal to kP divided by kD. So steady state error is equal to kT divided by kP. Okay, so if I have a type 1 system, or for this system, if my input is unit ramp, this is my steady state error. So what should I do to decrease my steady state error or improve my steady state performance? Either I need to increase kP or I need to decrease kD. Okay, this is also important because KD is like the D gain or derivative gain, which is helpful for stabilizing the system. But as you can see, it has a negative effect on steady state performance. So what I can do is, if I increase KD in order to satisfy steady state performance, I should also increase KP. Okay, that's nice. Okay, that's great. We already computed that also. So what is the last input type that is given in the problem is unit quadratic. So, and I know that since it's a type 1 system, for unit quadratic input, error steady state is simply equal to infinity. So it means that error will blow and will go to infinity. Okay, that's great. So I have one more example. Okay, so a couple of more examples. And as you can see, these examples are very straightforward. Okay, so this is my system. So I have PD controller. Okay, this is actually actual PD controller, KDS. Okay, so it's a very similar system as you can see. I just changed the topology. Okay, so both of them are types of PD controllers. Okay, R of T and Y of T, and the goal is same. I need to compute the type of the system. Okay, and characterize the steady state error to unit step, unit ramp, and unit acceleration. Okay, so GOLS is equal to simply 1 over S squared times, okay, no, sorry for that, it's true, but okay, so let's write this. Okay, 1 over S squared, okay, KP plus KDS. That's great. So I know that it's a type 2 system. So in the type 2 system, I have Ka, or static acceleration constant, which is equal to isolate S. Replace the remaining part with S equal to 0. It is simply equal to Kp. Okay, my static acceleration constant is equal to Kp. And I know that for unit step and unit ramp inputs, my error steady state is equal to 0 for both of them. For unit acceleration, my steady state error is equal to 1 over Ka, is equal to Kp. Okay, so if my input is a correct input, if I want a small steady state error, what I need to do is I need to improve my Kp, or technically increase Kp value. Okay, that's great. Okay, now let's solve another example, which is also very simple. Okay, that's great. That's nice. Okay, so another transfer function. Okay, that's great. Plus minus. Okay, so one transfer function here, S plus 1. And here I have equal to S over S plus 10. Okay, this is a slightly weird transfer function. It's not very common. You will see that. Okay, Y of T, R of T. So what we do is we compute the open loop transfer function. GOLS is equal to S divided by, okay, S plus 1 and S plus 10. Okay, so what is the type of the system? As you can see, we have S in the numerator, okay, which technically says that this is a high pass filter system. So the type of the system is equal to technically -1. It's a type negative system. But okay, so it's for a type negative system. What is the steady state error? We know that for unit step input, it's equal to 1 over 1 plus Kp, right? Okay, we know that. So what is 1 over 1 plus Kp? Plug S equal to 0, GOL 0 is equal to technically 0, so it is equal to 1. So what is 1? 1 is meaning that I have unit step input, which is equal to 1, okay? So R of T is equal to 1, constant steady state error steady state is equal to 1, which means that my output is going to 0. So I have 100% steady state error, which is super terrible. But type negative system doesn't exist in general for control system. This is just fictitious. It's just for teaching the material and understanding the topic. Okay, so for unit ramp and unit quadratic, I know that error steady state will be equal to infinity because it's a type negative, or like say the type of system is less than 1. That's good. Okay, so I have, I think, one more example. Okay, so two more examples. That's nice. Let's look at one of them. Okay, that's nice. So I have another transfer function. Okay, that's great. So this is plus, this is minus, Kp 1 over S squared, and this is my output, Y of T, and here I have R of T. Okay, that's nice. So what is the type of the system? Okay, GOLS is equal to Kp divided by S squared. Okay, so type of the system is true. It's 2. Okay, it's type 2. Type 2 system. That's great. So can we compute the steady state error? Okay, so if we try to compute the steady state error, we can say that error steady state for a unit step input and unit input is equal to 0, which is not the correct answer. Why it's not correct answer? Because I have double pole at the origin in this system. Okay, that's nice. That's great, but this is true for the open transfer function, right? Okay, but I didn't compute the y of t. Okay, I directly applied the final term. Okay, so what I need to check is the stability of the system. Okay, so if I compute y of s divided by r of s, okay, y of s divided by r of s, I will find that this is equal to what? Okay, so let's do that. Let's do that quickly. What's the transfer function? Okay, g of s, or let's say t of s of this system is equal to kp 1 over s squared. Okay, 1 plus kp s squared. Okay, that's great. Okay, that's nice. So I have kp s squared plus kp. Okay, so I computed the closure transfer function. What I found that I have two complex conjugate poles. Okay, so it means that I have a pole here, I have a pole here, which means that my imp system is bibo unstable. If I have a bibo unstable system, it means that the system is not stable, which means that for a constant input, I may not be going to 0, or I might be going to even technically. Okay, so what you need to check is the stability to ensure the steady state performance of a system. If we are not stable, steady state performance is meaningless. Okay, so if we technically compute y of s and y of t of the system, we will see that y of t is equal to 1 minus cosine kt, for t is greater than 0, which means that I have a sinusoidal or cosine signal, which means that I never reach a steady state value.